In this example, we want to find the eigenvalues and eigenvectors for the three images given here: 5, 6, minus 6, 0, 1, 0, 2, minus 1, minus 2. As always, I'll be looking at a minus lambda I and finding its determinant, which we get by subtracting lambda off the diagonal of this matrix. Find this determinant, we're going to expand along row 2 because there's only one non-zero thing in row 2. This becomes -1 to the 2 plus 2, that's the row 2 column 2 entry, times the 1 minus lambda, and then times the determinant of the minor of these four corner elements. We can find that 2 by 2 determinant, expand and simplify. We have plus 2 lambda minus 5, so minus 3 lambda. We have minus 10 plus 12 is plus 2. This is 1 minus lambda times lambda minus 1, lambda minus 2. So what I end up with here is a negative sign, lambda minus 1 squared, lambda minus 2. So my eigenvalues here are lambda equals 1, that's repeated, and then lambda equals 2. Let's do the known version first. Let's do 2. So for lambda equals 2, a minus 2i gives the following matrix, which I now want to row reduce. I can divide the first row by 3. Use the top row to cancel out the bottom one by subtracting 2 copies from it. I can now divide row 2 by -1 and then use it to cancel that 5 below it. And there's our good row of zeros we're looking for. So in equations, what did this say? Well, this says that v2 equals 0, and then v1 plus 2v2 minus 2v3 equals 0. So v2 is 0, this term is gone. And which is v1 minus 2v3 is 0, which I can do by picking v1 equals 2 and v3 equals 1. That'll make that go to 0. And so for this eigenvalue of 2, an eigenvector is 2, 0, 1. Now let's see what we get for lambda equals 1. If I do a minus I get the following matrix. To reduce, I'm going to swap rows 2 and 3 and divide the first row by 2. And then if I do row 2 is row 2 minus row 1, then I can divide row 2 by -4. So what does this tell us? Well, this tells us that v2 equals 0 from the second equation. And the first says that 2v1 plus 3v2 minus 3v3 should be 0. v2 is 0, so this term is gone. I'm up with just 2v1 minus 3v3 is 0. I can do that by picking v1 equals 3 and v3 equals 2. 6 minus 6. And so we get that for lambda equals 1, an eigenvector is 3, 0, 2. Notice for this, we only got one eigenvector, even though we had power 2 in the original equation. This is the case of a defective eigenvalue because we have power 2 for the algebraic multiplicity in the equation itself, but I only get one linearly independent eigenvector. You can try, there is no other way to solve both of these equations here without having it be a multiple of 3, 0, 2. As there is only one linearly independent eigenvector, and even though it had algebraic multiplicity 2, it only has geometric multiplicity 1, you have a defective eigenvalue here. That's fine. That's just all you get for the eigenvalue eigenvectors for this matrix. There's an example in the repeated eigenvalue case of what you can get for the eigenvalues and eigenvectors of these matrices, noticing what happens when you have a defective eigenvalue in this scenario.